Thank you, Johan, and thank you, everybody, for being here. I appreciate it very much that I'm invited here, and I take it that it has been a long 2-week sessions with many information accumulated, with lots of new knowledge coming up, which is very good, but also the fatigue piles up. And in that regards, I try today to deliver a session that would be a little bit less technical, however, I would hope equally as useful to you. So my name is Dimitrios Lyras, and I'm from Greece. I'm a principal data scientist with SAP, and I'm part of a global data science team comprised of more than 70 individuals with different kind of roles, like big data engineers, data architects, data scientists, visualization experts. And what we do is that we work closely with big companies. We understand business critical challenges that they face, and we provide solutions using AI and other creative thinking algorithms. So that, combined with my prior experience coming from an academic environment, having worked several years in R&D and similar projects, motivated me to deliver a speech today that would be in between the two worlds, that would highlight how all these nice algorithms that have been outlined so far by the speakers can be leveraged into actual use cases, into ways to tackle business critical challenges that modern businesses face. So that being said, I will now move on to the agenda, which would be fairly short. I would like mainly to guide you through some of the use cases that we have worked for, and maybe have a little bit of time for discussion later on. So the agenda would be as follows. First, I will try to address the question of why AI and how does it affect the modern business world. Then we will go over a few of the outlined use cases, and then I will conclude this presentation with some key home messages that I think would be good with regards to how we see these data science algorithms being applied in action and possible bottlenecks around it. So how is artificial intelligence affecting us? One quick and easy way to understand that is just to use Google. And if someone just starts typing what artificial intelligence will do, you will for sure get some positive and negative feedback. Like, for example, it will say that it will transform the university's work, or it can create new kinds of work, and these are positive. Some are a bit more negative in the way that they think, like it can replace humanity, and hopefully not. And coming up back to what Sharon told us yesterday about the ambiguity when using 60 languages, we will also see that artificial intelligence will smith based on the iRobot movie. Let's hope that not. However, I guess that it is a fact that data is transforming nowadays businesses. And maybe you have already heard of this quote, data is the new oil. And there's a lot of people now resembling data with oil, and I think there's a good reasoning behind it. Actually, I can find it very successful, very useful for two reasons. Not only because the data bring a significance equal to what oil brought a few years back, but also it has another common characteristics. If you think of it, we have, and me being Greek, I always like historical, let's say, references to history. And from Herodotus, we have mentioned that oil was used to build the Babylon towers. And for so many years, we never used of it until 150 years ago with the invention of the combustion engine that revolutionized our industrial business life. In a similar way, we always had data, but we didn't have the means to aggregate them, to refine them, to analyze them, and to convert them to something actionable. And that's what's happening today, and that's what businesses start to realize. This is just a few of the potential use cases that one could leverage machine learning algorithms in order to start answering questions. The most typical ones I have put here in a summary. Like, for example, we can use data to understand when a machine is going to fail. We can predict the quality of the delivered products. We can identify fraud in several transactions, or we can do any type of regression or classification forecasting about price optimization, about elasticity, about the demand or revenue forecasting. And of course, we can apply clustering for doing customer segmentation and understanding different trends in our customers, understanding churn, running MCMC analysis for assessing risk, and so on and so forth. And when these use cases are combined also with more means, with more media, like audio, video, images, then they can also extend to other use cases, like the ones that also employ deep learning techniques, like, for example, especially useful in the medical domain for health diagnostics, for automatic translation, for image captioning, or image-based analysis, anomaly detection. So these are only a few of the use cases that we have seen that they are trending across customers, and it makes no wonder why data science is such a desired skill. This is an overview of the top 10 industries on different parts of the world that clearly demonstrates that this is not trending for one specific industry, it is across industries. Everyone is interested in what's happening. So with that, I will now start going over together with you along several use cases that I have picked to discuss. Initially, I had more, but in order to make that fit in time, I have selected only 2 of those. If we have the time, maybe we can resume later on with more. So the first one that I'm going to speak about is coming from the public sector, and it is around crowd management. And what I'm going to discuss with you today is just a piece of the whole solution that was proposed. The whole solution also involves IoT devices, visualizations, predictive trends about inflow and outflow of people. However, here today, I would like to discuss with you one of the early challenges that we faced when we started engaging for this challenge. And before coming in the details of it, I would just like to outline for you, if you're not aware of about what crowd management is, it's the issue about trying to understand the people's behavior under different conditions. And this is quite significant as an issue. It's quite critical because you might have already heard of several incidents that have happened with people being accumulated in public spaces and then panicking for some reason or getting, let's say, an alarm of a terrorist attack, and then they just try to spread. And this can have vital consequences in lives being lost. So it's very important to understand if people are condensed in a specific place, then what is the risk that they undergo of suffering from a panic scenario or having casualties. And then there's a lot of questions that pile up. Like, for example, am I under risk currently? And if so, why am I currently under risk? And how can I overcome that? What would be practical solutions? The good thing for humanity is that we don't have lots of data. However, we would need to have more data in order to be able to come up with more insights around what drives answers to those questions. And in that regards, we came up with a simulation-based modeling. We say we will try to model the human behavior in such a way that when running those simulations, we will try to understand and answer those questions. In this slide, I very briefly highlight a brief overview of what the model parameterization and model input and output would look like. This was a toy example, an early stage simulation. And in that example, we have several input parameters, like, for example, how many people we will be simulating to be in that space, for how long we would like to run the simulation, and actually the topology of the space that the individuals would move on. And of course, then we have several other parameters, like, for example, the number of entrance points and of exit points, the preferred speed of people, if there are some blockage areas where they cannot transit from, and so on and so forth. In this part of the slide over here, you can see the distribution that we used, let's say, in order to sample preferred movement speeds from individuals. After doing some research, it's been said that on average people would like to move, let's say, with 5 kilometers per hour. And of course, it would be unrealistic to believe that everyone would follow that trend. So we had a skewed distribution that would let us sample possible movement speeds out of those individuals participating in our simulations. Here I will now play some animations about how these simulations looked like in those early stages in this toy example. And in this case, we're just simulating just a small corridor, sort of saying. However, it has only one extra exit point. And in this simulation, we simulate the inflow of 3,000 people with batches of 20 people per second. And we are trying to understand if this is a risky situation or not. And just to guide you a little bit in what we see in this slide, so that it becomes clear later on, each square, you can imagine that as a square meter of this topological rearrangement. And in each square, you can see several numbers like these ones and colors. This is assumed to be the individuals in that particular square meter. And the more condensed it is, the more red it will be depicted in the simulation. If it exceeds the number of 6 people per square meter, then this is usually deemed to be a risky situation. So just by letting the simulation run, we see how this model parameters motivates those individuals to start make rational decisions during the only exit point. And it's very soon that we start anticipating that we're having a clog there. So if this was the inflow and this was the only exit point, then we would soon run into a very risky situation. Which then poses the question about how can I resolve it? And by the way, if we just then visualize what was the actual movement in the simulation of the individuals compared to the originally sampled ones as preferred ones, we will see that they significantly differentiate. In fact, they couldn't move in a natural, let's say, walking speed, right? So that now poses the question of how can I resolve that situation? So for example, if I extend that to twice, this single exit to twice as much, then would that resolve the bottleneck? The answer is no. It would just procrastinate a little bit in time, but we would still suffer from the same situation. And then we got the following answers, the following questions. So, okay, so what can I do to resolve it? And then you start some exploration. Like, for example, and again, this is how in this simulation the actual movement compares to the preferred movement in this simulation scenario. As you can see, it's totally different. All individuals, or the majority of individuals, keep walking on a much lesser rate than the preferred one. If, however, I just make the exit 4 times as much as initially assumed, then we can see that this is a good scenario that can handle the inflow rate, and people are in a risk-free scenario in that case. And in fact, this is also demonstrated by this side-to-side chart. The actual movement now is much closer to the originally sampled one. But then we got the following customer question, but how about if I cannot topologically make that big of a space, if there are some other obstacles that disallow me to do that? And then we can run different scenarios. We can start investigating different possible solutions, like, for example, the one of opening opposite exit doors. Because, again, assuming that people use this rational logic about moving the shortest path, sort of saying, then as we can also see from the simulation, they would start splitting apart. So even if we do not have this opportunity to, let's say, extend it to a much bigger length, then just by doing some simulation studies, we can find out optimal endpoints that we can also release or make some topological rearrangements that would help decongest the issue that's about to happen. Again, in this simulation, we can see that, again, it's not as good as it was before, but it's very close to the preferred movement speed. Last but not least, we can also play around with different model parameters, and we can say that if you are stuck and you cannot do any of those changes to the topology of the space, then you can also find out what's the minimum or actually the maximum inflow rate of people so that you can be in a risk-free scenario. And in this simulation, again, we can see that we will be resolving all clogs, but by halving the inflow to 10 people per second, right? And again, not a perfect fit, but much closer to what we would like to see. So this is the wrap-up of the first use case that I will share to you, which is, again, as I say, a small toy example of a bigger solution. However, that allowed us to get with several potential benefits. First of all, it allows us to understand or simulate and approximate how the human behavior works in an environment where we can set our own parameters. And then we can run either a heuristic or a graded search and identify possible solutions to overcome risky scenarios that are about to happen. We can even use this kind of simulation tool to map it back to previous scenarios where we had incidents and run a root cause analysis, find out what was wrong, what was actually that happened back then, and maybe find ways to overcome those challenges. With that one, I will now pass to the second use case, and this is from a different industry. This comes from the manufacturing industry, and it's about how we can improve the quality of the delivered products and also improve on the predictive maintenance landscape. And for that use case, I want you all to imagine that this is about manufacturing. So there's a huge production line that creates thousands of products per minute. So it's super fast. What happens is that they have these CAD mechanisms that they take snapshots of the products as it goes through the production belt, and they do some ad hoc analysis, and if the product does not conform to some standards, then it's rejected as scrap. And when this happens, this is a reject event, right? And it can happen due to several reasons. They have, the customer has classified different reasons around whether the QA mechanism would discard some of those productive items. However, what happens is the following. Such reject events could happen because, as I say, this production line runs very fast. And some of them could be normal. Like, for example, the item could be accidentally misplaced on the production belt, or the snapshot might not be so clear. So this is not something to worry about, and the operator would not stop the production line, which actually has an increased business cost for businesses. However, there are other cases where these reject events, especially if they pile up, there are some early warnings about a more critical event that's about to happen, and that also jeopardizes the quality of the end product. So what the customer told us was, what I would like to know is that when I observe a reject event, I would like to know, is this normal or not? Should I stop the production line? Should I do a corrective action to prevent a quality degradation, or this is okay? And also the process engineer had a different set of questions to answer. Like, for example, how can I improve my production line? And why two seamlessly identical production lines behave so differently? This one seems to be much robust than the other one. So can I copy practices from one to the other and see what can work? I'm not sure if you've seen or read a similar analysis before, but I can tell you it's true. The majority of the modeling part is, in the majority of the use cases, the true modeling on algorithm design is only a tiny part of the whole piece of the equation. In particular, there is a big tendency to spend a lot of time in data preprocessing and in business understanding. We will come back to this discussion even at the end of this presentation. So this is again what happened in this case, and you will realize why. The first thing is that we need to bring together a lot of data. Usually, we do not have one data silo. We have many different kinds of data that bear information to the question that we're trying to address. In this particular use case, we used 4 different data sources. We used, of course, the process parameters, which is thousands of measurements, as I said, running continuously on every single second. We have camera data of the products that run on the production belt. We have downtime information that highlights how often the operators stop the line and what do they do when they do that. And, of course, maintenance data about how often do they replace part, what do they replace, and so on and so forth. And, of course, I wish things were as easy as they look, but like everything in life, it wasn't. One big part is about massaging the data and printing them in a format that could be actionable. Like, for example, we have different sampling rates, we have a lot of noise in the data, there's a lot of outliers that need to be detected and eliminated, a lot of missing data that we need to anticipate if we should remove them, replace them with some different way or statistical way to come up for that particular use case, as we've seen in the previous lecture. And on top of that, we need to engineer new features because, for example, knowing that a part was replaced yesterday is not good enough. For example, for this particular use case, we need to engineer, let's say, the maintenance adherence. So if the manufacturer says that you need to replace this part every week, did you stick to that? Did you skip some maintenance services? And how adherent were you to the recipes? Or gradients of change, how easily do things degrade? So these are just some things that you should be having in mind when working with actual business use cases. The data are not the ones that we tend to pick, are the ones that are readily available there. And usually, they are not in the format that we would like to use. So a big time is about understanding how to shape them. After having done that, one other thing that was critical in this particular use case is that we didn't have a clear, let's say, labeled data set. As I said before, you can imagine that several reject events happening, Some of those are critical and the operator acts upon them, the other ones aren't, and they just let it go. So we need to define the target, and we need to understand what is the problem, what is critical. And we had 2 questions to answer, these 2 questions that appear at the bottom of this slide. So from all the reject events, or all the reject reasons, which are the most critical to start working on? And if we know them, what is the effective number of reject events that when you see them, you would stop the production line? We asked the experts, we asked the operators, and the reply was confusing. They said that this is empirical. If I see a few of those happening in several minutes, I would worry about them. If I see them happening within a day, then maybe I wouldn't stop them. And we say, do you have a golden book of truth of what's exactly this number to go back and see in our data? How many abnormal situations do you have and how many normal ones you have? And they said, no. On top of it, these numbers change per production line and per reject code. So you need to find that out from the data. And that's what we did in order to identify which ones of the 200 reject reasons was the most important ones. We came up with some metrics. We devised these metrics, and we say that any reject event that we will try to address in this approach should be chronic. It means that it happens now and then, and it's not a sporadic event. It should be forecastable in the sense that we have information from the data sources that I told in order to see what's going to happen in the future. It should be fixable in the sense that if the operator acts upon it, then we see this being fixed. And of course, it should be viable. At the end of the day, it should bring actual revenue, additional revenue to the business. And some of those metrics are quite easy, are quite straightforward. You just look in the data, you just plot them, and that's like that. For other ones, like for example, fixability, we needed to improvise a little bit and come up with our, some ad hoc measures. Like for example, we said in order to account for the fixability of reject events, we will just see cases where we had a line stop, and before the line stop, we had an excess of reject events, and then this cooled down. So just by doing a simple aggregation and just coming with a ratio, we can a little bit quantify of how often this issue was resolved after a stop. So in that sense, we were able to find out which reject codes to focus. Then we had to answer about what's the minimum number of reject events that most usually an operator would stop the production line and act upon them. And based on the definition that we got from the experts, we came up with the idea that this looks like a Poisson distribution underneath the data. So they said that normally I would expect some of those reject events to happen on time-independent intervals and at a constant rate, right? So we said, if we knew that, and maybe we had, let's say, distribution like that, then we could start asking some statistical significance questions. Like, for example, if this is my underlying distribution of data, then how possible is it that I see 10 reject events happening within 10 minutes? How possible is it that, how probable is it that I see 20, and so on and so forth? And that way we could tune the statistical significance. However, as I said before, these Poisson distribution assumptions are not fully met because the data that we had are quite heavily noisy. They also contain a lot of reject events for which the operator didn't act immediately, and these are hard to discriminate. You cannot know if this is part of a critical situation, of an ongoing critical situation that the operator didn't act upon it, or indeed it describes the normal operation standard. And that's the way we had to improvise a little bit and come up with a more relaxed version of the Poisson assumptions, where we adjusted the significance thresholds based on the feedback that we got from the SMEs, and also based on some empirical evidence that we see in the data. With that approach, we were in a position where then for each production line and for its reject code, we could identify a threshold that would tell us that if, for example, for line 1 and reject code 33, I see more than 11 events happening within 10 minutes, then this is abnormal. If it is less, then this is normal. And with that knowledge, then we could go back in our dataset and label each of those reject events, and then we had a training dataset to start working on the predictive landscape, right? Now we knew what was the process parameters, what were the maintenance parameters, and some reject events that are abnormal, and some other cases where the reject event was normal and the operator wouldn't act upon it. So we came up with an idea that creates a holistic overview. The three main components of this solution was the triage, diagnosis, and treatment scenario. You can imagine as a solution where the operator, as the production line runs, when a reject event happens, they would like to see an alert that they would say, that they would tell them, you shouldn't worry about it, this is normal, it can happen, or this is abnormal, and if you don't act upon it, then a lot of more of these reject events are about to happen in the next 10 minutes. You might have a quality degradation. But then the customer said, okay, if I know that, then it's good, but not good enough. I need to know why. And again, this is a discussion that I also had with some of you yesterday. Like some of these models, when we apply them, they're very, very good, but the customers also want to have interpretable models. Like, for example, if I apply PCA on the features, and then I tell them that I see this abnormal situation, most likely due to component 37, then they do not know what to do with that. They do not know how to act upon it. So it should have, let's say, a way that they can also have a diagnostic information about how they can act upon the abnormal situation. And last but not least, about treatment, and that's the holy grail of the whole solution. So we got a customer quote that I have here, like I would like to have a Ronald on every plan. And Ronald is a very skillful operator that had the best resolution times. And he said, how about if I could replicate his knowledge? And we said, okay, now that we have data, we will try to address all of those questions. For the first two ones, we used ridge regression. And as I said before, there are multiple models that we could use for that regard. However, we came up with a model that first we tried a simple one that's also interpretable and effective to handle these millions of records. So we're speaking about big data issues here. And the good thing using the regression equation is that we can get, I will demonstrate how we can get most of those answers that in the questions that I posed before. Like, for example, just by looking at the actual score of the regression equation, I can quantify how critical an event is, and I can then render that to an educated decision about whether this is a critical event or not. Or, if I combine it with feature elimination, I can also identify which parameters are most important that drive my decision, right? Especially if I started, let's say, with a few thousands of parameters, and then some of them were eliminated, then I could turn on and say, these are the most important ones that you should be focusing on, not all the thousands of those. And last but not least, we can also quantify the importance of those parameters, and then provide a ranking list for the operators to know where to look up. So with just one model, we can also have the predictions and the key drivers analysis. We can have the triage and the diagnostic tool. For the sake of our modeling perspective, we used a library that is in-house within SAP tools. It's called Automated Predictive Library. And the good thing around it is that there are many things when doing predictive algorithms for business use cases that need to be taken care of. Like, for example, you can see here all these yellowish highlighted activities that need to be accounted before applying any predictive model. Like, we need to assess the collinearity between variables. We need to numerically bin variables. We need to convert them to, if they're categorical, to one-hot encoding. We need to do this training split and validation testing split. And we need to quantify the results. So there's a lot of things that need to be done. And when done in a corporate framework, then this needs to be operationalized. And that's why we came up with the idea of using that in-house algorithm. For the later part, however, we could not use ridge regression. For the recommender engine, we needed to come up with a different model that, again, would exploit the historical data and will let us come up with a solution around it. So for that one, we used another library that's, again, within the SAP ecosystem of algorithms. And there's in-house implementations of most of the data science algorithms that might be needed. For this second use case, we used KNN. Again, we reverted with a lazy learner. However, it was simple in the idea, but very effective in letting us come up with this recommender engine. And to let you, to make more clear how the recommendation engine would work in this case, I will just go over this slide. As you can remember, the situation so far is that we have the process parameters. This is the observable information that we have. And we have a reject event happening that we can now flag it as normal or abnormal, as critical or not, right? So if critical, then I need to know how to act upon it. And of course, if there is a solution problem database, then I can use that one, but most often there isn't. So what we did was that we said we will go back and look in all cases where there was an effective problem resolution. You can imagine, for example, this use case depicted in this slide. And you can see here, for example, we had this critical event happening, and then there was a light stop, then some adjustment happened, and the problem is resolved. Then for each one of those reject events, I can go and map it back to the individual process parameters that were happening at that exact time. So I can now fingerprint the reject event to some process data. And then what I can do is that when I have a new reject event, and whenever my predictive model tells me that this is abnormal, then I can use KNN in order to compute the distance between this new reject event compared to all the historical ones. And if, for example, I would use K equal to 1, then I would find, for example, that for this new event, this would be the closest resembling incident. So I could go back in the data and find out what was the corrective action that was performed back then in order to create this issue and replicate the same logic again. So that was the idea. And last but not least, it's about how to bring all this together in a way that can help not only take benefit of all these models that are underlying the solution that we devised, but also come up with a way that can improve the models in a way that the operators would feel comfortable with. And here you can see a UI, well, actually a mock-up of the UI that we delivered that highlights the simplicity, yet the outcomes of all those models. Like, for example, they could see in a single screen all the abnormal events happening with an assessment of the confidence of the model. They could get a sorted list of what is that drives this specific reject event, and maybe they would like to look on their own in those contributor analyses. And then we have a sorted list of recommended actions. And the good thing around it is that we said, okay, now that we have that one, let's make it easy for the operators to give us some better training data to overcome the issues that I discussed at the beginning. Like, for example, tell us, do you agree with this abnormal score or not? Is it good enough or not? And with that approach, later on, we can have better training examples, better training incidents about what reject events are critical and what are not. Or, for example, we could say, which of these actions did you use? And which were successful? Which ones didn't? And which one can be further improved? And if there's anything that's not there, just give it back to us. And the model can then later on improve, and on the next iteration, it can pile up with this new knowledge. So what I would like to have in mind, I would like you to have in mind from this use case that I described is that, as you can see, in most of the cases, the data that we have to work for are not of good quality. We need to think outside of the box in order to come up with solutions to overcome those challenges, and also make sure that knowing what we're aiming for, we can accumulate better data in a better time framework so that we can also improve our models. So with that one, I will now just also highlight some other, a few ideas that I have also found to, let's say, be a small gap between an academic and a purely business environment. I'm not sure, has anyone of you seen the CRISP-DM strategy before? Okay. So this is the main standard that we currently use for running data science project, and it's an across-industry standard process. What I want to specifically highlight is two things, actually. The first one is the business understanding. Very often, as data scientists, we are very eager in working with the data, and we forget what's the critical questions to be answered. So it's important when you start working on a project to understand exactly what you're trying to solve, to quantify how it's going to be successful, how success will be measured, and when this would be enough to validate the business requirements. And in that regards, then you can ask for the right data, or you can massage the data in such a way that can address those questions that you have understood very thoroughly. And this is the data preparation step. And upon having a unified data model that satisfies those conditions, then we can do the predictive modeling part, and of course the evaluation. And the evaluation, again, is not only about accuracy. Some of the businesses, as I told you before, might disregard a better model in the view of a slightly worse model that is actionable or more transparent. So it's important to evaluate, as I said, the outcome of those modeling approaches, not just by looking on some of specific metrics, let's say, or a performance metric, but also in the overall KPIs that have been defined in the business understanding scenario. And this is an ongoing process. It's an iterative process that should be validating, should be updating, And until we feel confident that we have, let's say, a first model to start working on. Then we can deploy it in production, and it doesn't end there. It should be monitored, updated, and then this cycle continues again. So this is the idea around it, and this is actually a common, let's say, error, a common mistake that we see often in clients. They say, okay, now I got it. So what I need is a data scientist or a team of data scientists. And what they usually do is that they hire a bunch of people, they put them in a room, they say, okay, I have problems, take my data, come after a month and tell me what to do. This doesn't work. This kind of people, if they don't understand exactly what's critical to the businesses, they may come up after a model, after a month with a model that just increases, let's say, something by 1% or by 2%, which doesn't make any sense for the company to invest on. And then the outcome is, okay, data science doesn't work for me. No, it's important to have this complete life cycle, as I described before. And it's not only that. The data science part is a piece of the whole equation. It's a piece of a whole ecosystem of activities and of people that should be cooperating in business environment in order to make effective data science solutions. Like, for example, as you can see here, there's a pipeline that goes from the data access and data storage issues. So how are the data coming to me? Are they real time? And what is real time? We even have customers that needed to relocate closer to the servers in order to achieve the near real time, because millisecond could be critical for their businesses. So data access and data storage is quite vital. How you prepare the data and how efficiently can you do that in the view of new data is also important. Of course, the data science part, and visualize them to understand them, not only us as data scientists, but also disseminate those outcomes to the business users that can help us understand, again, what's the next big goal, what's the next big step to focus on. And of course, that could lead to some valuable insight later on. And again, this is a repeated cycle. And as you can see, it involves different people coming together on the same table, different people with different backgrounds needed to cooperate. So imagine having to put together in a room an IT guy, a data science guy, a business user, a BI analyst, every week, just to discuss again the new updates that should be happening. This is something that we should have in mind. So it's not about writing an ad hoc solution that works well on our computers. We should have the whole ecosystem of activities end to end in order to make that successful for a business framework. So with that one, I would like to thank you very much for your time and give some time for discussion or for any open questions if there is any. The key take-home messages that I would like to have from these presentations are the following. Well, first, that data science has been said to be the sexiest job of the 21st century. I'm not sure, we're losing to robots. But it's actually a trend that it's actually a fact that data science is not a hype. It's something that businesses embrace more and more, and through that, they open new opportunities. They expose themselves to new business models, and they create more and better services for our customers. It's important, however, when engaging in data science activities with the businesses, to have a very clear understanding of what our challenges are, to not work in silos, to be open to discussing with other teams, to merging multi-source of information, including audio, image, video, process data, maintenance information. Sometimes we need to think outside of the box. There will be lots of difficulties when compared to, let's say, us picking the data that we want to work with rather than getting the data from the customer. But with goodwill and knowing exactly what we are doing, we can be successful in that regard. So with that one, thank you very much for your attention, and I will be willing to take any questions. Thank you.